Neurotransmitters are the endogenous ligands, that is, they come from our own bodies and bind to receptors to cause biologic effects. Drugs are exogenous. They are something that we take or are given that can influence synaptic transmission. You can broadly categorize a drug as an agonist or an antagonist based on what it does to neurotransmission. An agonist mimics or enhances the effect of an endogenous neurotransmitter. Conversely, an antagonist prevents or decreases the effect of the neurotransmitter. It's important to note that I'm not using the word block here for antagonist, because as we'll see later, you can block or prevent an individual stage of synaptic transmission, but still be an agonist in terms of the final effect on communication between two cells. Let's think about the stages of synaptic transmission. Neurotransmitters first have to be produced. The enzymes and precursors are sent down to the terminal via exoplasmic transport, and neurotransmitter is produced right at the terminal. Neurotransmitter then has to be packaged into vesicles using transporter proteins. Neurotransmitter is released into the synaptic cleft when vesicles fuse due to synaptic activity, that is, due to an action potential reaching the terminal, calcium entering and facilitating vesicle fusion. Once neurotransmitter has been released, it can bind to postsynaptic receptors to cause an effect on the postsynaptic cell. And neurotransmitter can be eliminated from the synapse, for example, by enzymatic destruction or reuptake. So let's think about what an agonist would do at each of these steps. Remember that an agonist is going to enhance or mimic the effect of a neurotransmitter. So increasing neurotransmitter production would be something an agonist would do. If more neurotransmitter is produced, there's more available to communicate with the postsynaptic neuron. Similarly, an agonist would enhance neurotransmitter transport into vesicles. Conversely, an antagonist could prevent neurotransmitter from being packaged into a vesicle. If there's no neurotransmitter in the vesicle, there can't be any released. And an antagonist could use that strategy to reduce synaptic transmission. An agonist would enhance release of neurotransmitter into the synaptic cleft, again to facilitate communication between the pre- and postsynaptic cell. Enzymes would destroy neurotransmitter, preventing it from binding to postsynaptic receptors. So an agonist would decrease enzymatic destruction to make more neurotransmitter available to communicate with the postsynaptic cell. An agonist might mimic the effect of a neurotransmitter on a postsynaptic receptor by binding to that receptor and activating it. Another way of eliminating neurotransmitter is through reuptake into the presynaptic cell. An agonist might prevent neurotransmitter reuptake, again making more neurotransmitter available in the synaptic cleft to communicate with the postsynaptic cell. We can also categorize agonists and antagonists as direct or indirect based on how they influence synaptic transmission, that is, on which stage they influence synaptic transmission. A direct agonist would bind to and activate the postsynaptic receptor, while an indirect agonist would facilitate synaptic transmission via some other process. A direct antagonist would bind to the postsynaptic receptor, and while it would not activate the receptor, it would still prevent the endogenous neurotransmitter from binding. An indirect antagonist would decrease synaptic transmission via some other process. Here's an example of a direct agonist. Beta endorphin is the endogenous ligand for the mu-opioid receptor. It will bind to the mu-opioid receptor and activate it. Morphine is an exogenous drug. Morphine can also bind to and activate the mu-opioid receptor, making it a direct agonist. Although morphine binds to and activates the mu-opioid receptor, there's another drug called naloxone that can bind to the same mu-opioid receptor, but instead of activating it, it will simply block the receptor binding site so the neurotransmitter or the agonist cannot bind. Here again we see morphine binding to the mu-opioid receptor and activating it. Now when we give the drug naloxone, naloxone binds to that same site on the receptor, but the receptor is not activated. However, the receptor is now unavailable for either the endogenous ligand, beta endorphin, or the exogenous agonist, morphine, and prevents those drugs from binding to the receptor. We can further categorize drugs as competitive or non-competitive by where they bind on the receptor. A competitive drug, a competitive agonist, would bind to and activate the postsynaptic receptor, while a non-competitive agonist would facilitate neurotransmitter binding to or activating the receptor via some other site. A competitive antagonist would bind to the same site on the receptor that the neurotransmitter would normally bind to. Again, it doesn't activate the receptor, but it prevents the endogenous ligand from binding. A non-competitive antagonist could bind some other site on the receptor and cause, for example, a conformational change to prevent the neurotransmitter from binding to its binding site. Figure 4.8 in Carlson and the surrounding text describes the difference between competitive and non-competitive binding. In competitive binding, we see the drug stealing the neurotransmitter binding site. A competitive agonist would then activate the receptor, while a competitive antagonist would not activate the receptor. When we look at non-competitive binding, we see that the drug has its own binding site on the receptor. The drug can then enhance, in case of an agonist, or decrease, in the case of an antagonist, the ability of the neurotransmitter to activate the receptor, potentially by changing binding affinity or something of that nature. For an antagonist, you can have a direct but non-competitive drug. Here we see a receptor with an agonist that would normally bind to and activate the receptor. Now we have an antagonist with its own binding site. It's non-competitive because it's not stealing the agonist binding site. But when the antagonist binds to its own site on the receptor, it causes the receptor to change shape. That is, a conformational change in the receptor. And now the agonist binding site is no longer available. Another example of non-competitive binding is an example of an indirect agonist that enhances binding affinity. Here we have a neurotransmitter binding to and activating, in this case, an ionotropic receptor that opens an ion channel. The agonist has its own binding site on the ionotropic receptor, and in the presence of the agonist, the receptor has a higher affinity for the neurotransmitter, making it more likely that the neurotransmitter will bind and activate the receptor. You could also have an indirect non-competitive antagonist that binds to the receptor inside the ion channel, preventing ions from flowing through the channel, even though it has not influenced the ability of the neurotransmitter to bind the receptor. It still makes the receptor non-functional. Again, when we think about indirect drugs, an indirect agonist can facilitate synaptic transmission by any of the other stages in the process, and an antagonist might decrease synaptic transmission by any of those stages. For example, an agonist might increase neurotransmitter release. You'll have to forgive me for the animations. Of course, neurotransmitters are not just released like that from the presynaptic terminal. They would be released as vesicles. But for the purposes of this exercise, I simply wanted to show that in the presence of the agonist, we have more neurotransmitter released, meaning that synaptic transmission has been increased. In contrast, an indirect antagonist might prevent neurotransmitter from being released, preventing communication from occurring between the pre- and postsynaptic cell without directly binding to the postsynaptic receptors. Normally, neurotransmitter can be taken back up into the presynaptic terminal using ATP through a reuptake transporter. A drug that blocks reuptake would allow more neurotransmitter to be available in the synaptic cleft to bind postsynaptic receptors. So a drug that blocks reuptake is an indirect agonist. Some neurotransmitters are also eliminated from the cleft using enzymes that would destroy the neurotransmitter. You could have a drug that would interact with the enzyme, preventing neurotransmitter destruction. Again, this allows more neurotransmitter available to bind and activate postsynaptic receptors. So a drug that prevents enzymatic destruction is also an indirect agonist. To summarize, an agonist will either mimic or enhance the effect of a neurotransmitter. Antagonists, on the other hand, prevent or decrease the effect of a neurotransmitter. This is a useful figure to look at the stages of synaptic transmission and what an agonist or an antagonist would do at each stage.